Hello everyone, welcome back to the channel. In this series, we reverse engineer the engineering behind apps we use every single day. In our previous episode, we explored how a ride booking app finds the best driver in just few seconds. Today, we are going to answer another fascinating question. How does Google Maps find the fastest route? At first, it might seem simple, but the engineering behind it is surprisingly clever. And by the end of this video, you will understand not only how navigation system works, but also how one of the most famous graph algorithms is used in the real world. Imagine you are driving to work. Google Maps gives you two possible routes. The first route is only 8 kilometers, the second route is 11 kilometers. Naturally, you would expect the app to choose the shorter one, but instead it recommends the longer route. Why? Here's the first surprise. Google Maps isn't trying to find the shortest distance, it's trying to find the fastest journey. And those two things are often very different. In this video, we are going to build a simplified version of a navigation system together. We will start with the real world problem, learn how a computer represents an entire city, understand the algorithm behind route selection, and finally implement everything step by step in Java. So, let's begin by asking a simple question. How does a computer even understand a city? At first, finding a route seems easy. Imagine a small neighborhood with just a few roads. Choosing the fastest path doesn't look very difficult. But Google Maps isn't built for a single neighborhood. It has to navigate entire cities, countries, and even continents. Suddenly, what looked like a simple problem becomes one of the biggest engineering challenges in modern software. Let's keep the city small for a moment. Here is your home, and this is your office, and we have a mall here, and let's say a school here. So even in this tiny map, there are multiple ways to reach from your home to office, either by route 1 or by route 2 or by route 3. So you might think, why not calculate every possible route and simply choose the fastest one? Here's the problem. Every new intersection creates even more possible routes. Add 10 more roads and the number of possible combinations increase dramatically. Add 100 or 1000 and checking every possible route become completely impractical. A real city contains tens of thousands of intersections. That means number of possible paths is enormous. Brute force is no longer an option. Now imagine opening Google Maps, typing your destination and waiting 30 seconds just to get a route. Most of us would close the app before it finished. Navigation systems don't just need to find correct answer, they need to find it almost instantly. So let's come back to our board. So checking every route isn't practical. Maybe we are asking the wrong question. Instead of thinking like a human, let's think like a computer. Does a computer need to know about buildings, parks, or restaurants, or even road names? Or does it only need to know how everything is connected? This simple idea changes everything. Now let's look at this city from our perspective. Now we see homes, then we see office buildings, we see restaurants, traffic signals, we also see road names, then fuel pump. That's how humans understand a city. But computers don't think like humans. A computer doesn't care whether this building is a restaurant, a hospital, or shopping mall. It only cares about one question. How do I move from one place to another? So let's remove everything that isn't needed. We don't need building names. We don't need shops. We don't need parks. We don't even need to know road names. What really matters is where road connect. Those connection points are the most important part of the navigation system. Every navigation system becomes a point. In computer science, we call these points Nodes. A node simply represents a location where a decision can be made. Should we go left, right, or continue straight? Every one of these decisions happens at a node. Now look at the road connecting two points. In computer science, this connection is called an edge. Every edge represents a road, and every edge has a cost. That cost might represent the distance and travel time. Something interesting has happened here. We have taken a real city and then transformed it into something much simpler. This structure is called a graph. To us, it looks like a circle connected by lines. But to computer, it represents an entire city. Millions of roads reduced to a simple network of connections. Notice what we have achieved here. We didn't lose the important information. The computer still knows which intersections are connected and how much it costs to travel between them. But now the problem has become much easier to solve. Instead of searching through entire city, the computer only needs to search through a graph, and that changes everything. We now have a map the computer can understand. But one question still remains. Out of all those possible paths, how does it choose the best one? That's exactly what we will build in the next chapter. We now have a graph that represents our city. Every circle is an intersection and every line is a road. And every number represents the estimated travel time in minutes. Our goal is simple. We need to travel from office to home as quickly as possible. But where should we go first? Imagine you are standing at your home. You don't know the entire city. All you know is the roads directly connected with you. Now that's exactly how the algorithm starts. It doesn't magically know the best route. Instead, it begins to check each intersection at a time. At the beginning, we only know the travel time to the neighboring intersections. Home is 0 minutes away because that's where we already are. Reaching B takes 3 minutes, reaching C takes 4 minutes. Everything else is still unknown. So, which location should we explore next? The closest one in this case, that's B. This simple decision is repeated again and again until every possible route has been evaluated. Now that we have reached B, we discover new roads. Some of them leads to places we have never visited. Others may offer a shorter route to an intersection we already know. Every time we discover a better path, we simply update our information little by little. The fastest route begins to reveal itself. But here's another challenge. How do we always know which intersection should we explore next? We need a structure that always gives us the location with the smallest travel time. This is exactly where a priority queue becomes useful. It automatically keeps the closest intersection at the top. So instead of searching the entire list every time, we always know where to go next. The algorithm continues exploring one intersection then another, always choosing the closest unexplored location. Eventually, it reaches the destination, and because every possible shorter route has already been considered, we know the answer is optimal. Every time you ask for directions, the navigation system performs this process behind the scenes. But understanding the algorithm is only half of the story. Now let's build a simplified version ourselves using Java. We now understand how the algorithm thinks. The next step is teaching the computer to think the same way. But before writing the algorithm, we first need a way to represent our graph in Java. One option would be a matrix, but in a real city, most intersections connect to only a few nearby roads. That's why adjacency list is much better choice. It stores only the roads that actually exist. To keep this edge information, we will create a class edge, and this class will have two attributes. One is the destination. Second is the weight of that edge, or in our case, the travel time of the edge. Now every road connects one intersection to another, and every road stores its estimated travel time. Again, to keep that information, we will use a map. The key here represents an intersection, and the value is a list of all roads leaving that intersection. In other words, every node knows its neighboring nodes. Now, remember the question from the previous chapter. We always wanted to explore the closest intersection. In Java, that's exactly what a priority queue gives us. The smallest travel time always stays at the front. We also need to remember the best travel time we have discovered for every intersection. At the beginning, only our starting location is known. Everything else is considered unreachable. As the algorithm discovers better routes, the values are updated. We get the current node, then we loop through the neighbor, calculate a better distance, if the new distance is better than the current, we will update the map, and insert into the queue. Notice something, we never pasted the entire algorithm. Now this is exactly what navigation engine is doing. Every update improves our understanding of the city until the fastest route finally emerges. Congratulations! We have successfully built a simplified navigation engine. Given a graph, It can find the fastest route between two locations. But here's an interesting question. If this is all Google Maps does, why does it feel so much smarter? The biggest difference is that the real world never stays the same. Roads become congested, accidents happen, constructions begin, weather changes driving conditions. Every one of these events changes the cost of traveling on a road. Now, instead of calculating the route just once, the navigation system continuously updates its information. Every time road condition changes, it checks whether another route has become faster. That's why your route sometimes changes while you are driving. Modern navigation systems also use many additional techniques: faster search algorithms, massive distributed databases, live traffic collected from millions of devices, historical traffic patterns, and machine learning models that improve travel time estimate. All of these work together to give you directions in just a few seconds. But underneath of all those optimizations, the fundamental idea remains the same: represents the world as a graph and search it intelligently. One of the biggest lessons in software engineering is this: we rarely start by building the most advanced system. We start with a simple, correct solution, understand it deeply, and then improve it step by step. That's exactly how many real world systems evolve. Today, we discovered how navigation systems transforms an entire city into a graph and use intelligent algorithms to find the fastest route. If you enjoyed this deep dive into real-world software engineering, don't forget to like the video and subscribe for more episodes in this series. In our next video, we will reverse engineer another everyday application and uncover the engineering hidden behind it. Thanks for watching, and I will see you in the next one.